This is the second in a number of webinars. My name is Ralf Hustad. I work for Luxinnovation, and together with LuxProvide and the University of Luxembourg, we're the National Competence Centre in Luxembourg for supercomputing. So today's episode is on everything you wanted to know about supercomputers and never asked. And I'm happy to welcome Julien Schleich for the presentation. So Julien has a PhD in computer science. He has been CTO of a fintech startup and is now HPC research scientist at the University of Luxembourg, among other interesting things in his vita, but I think that would be too long to cover it over here. So in case you have questions, just drop them in the chat. There's a tab for questions. If you can't watch the whole episode or would like to watch a previous one, we make them available on YouTube. Just look for Supercomputing Thursdays and you'll find them. There's also some more from the previous years with my colleague Ramona. On another topic, apart from our webinars, we also have smaller sessions in person, typically with a stronger focus on verticals. And of course, we have our large Supercomputing Day at Mudam on May 4th with a number of really interesting presentations. So if you're interested and haven't gotten the invitation, please do reach out. That having said, I'd like to hand over. Julien, the floor is yours.
Thank you, Ralf. Right. Okay, so this presentation is really an introduction to supercomputers, or what are also known as HPC, so high performance computers. And I'm going to be presenting three main questions. If you, oh, my bad, it's me. So I will first start by asking the question, why do we use supercomputers? In which situation they are relevant? Then I will take some time to present what are supercomputers and what's the difference with your personal computer. And then I will do a quick non-technical part or section about how to use a supercomputer. What's the general workflow to use it. So first, why use supercomputers? There are different use cases. One could be that running one experiment takes too long, or one computation takes too long on your own machine, and you would want to run that on a more powerful machine to speed up that process. The second one would be your experiments, when you run one, it's fine. It takes some amount of time, but it's okay. But you need to run hundreds or thousands or tens of thousands of experiments because you need to explore a lot of variation in the parameters, or you need to have some statistical confidence in your results. The third use case is when you can run your experiments, but on pet project, on small experiments only. It's when it's small, it runs fine. But as soon as you want to address real size experiment, it is either too long or not possible. Maybe you don't have enough memory, or the amount of time is just very big. So for each of those use cases, I took small examples based on some of the activities I'm doing at the University of Luxembourg. And those activities are based on the support tickets that we receive. So one person came to me and said, okay, my program takes too long on my machine. And he explained me that what he was doing is he had one very large file containing billions of lines with text. And for each text, he needed to run an algorithm that detects the language. So one simple solution in that case would be to take all the different lines and split those lines on multiple machines. Each machine would then process a subset of those lines, and that would, let's say, solve the problem of running on one computer. The second use case was running one experiment is fine, but you need to run thousands of experiments. We encountered that on one project at the University of Luxembourg, where we needed to do some protein folding using AlphaFold from Google. And doing one experiment was okay, it took between 30 minutes to a few hours, but they had a lot of different experiments to run, namely here 16,000 experiments. And so in this case, we distributed the load on multiple machines. Another issues that happens a lot on HPC is that you want to simulate experiments. You want to simulate physics experiments. And when you run that, when you want to simulate a small number of particles, that works fine. But when you want to simulate a real life number of particles, it's just too much for your local machine. And in that case, you also need to distribute the computation of, so the simulation of all those different particles on different machines. But in this case, you also need a lot of coordination between the different machines, because the impact of the simulation of one particle may impact the particle on other machines. So that's three use cases that usually are encountered and are useful to for the HPC. So we need to run those experiments on a supercomputer or on the HPC, and you might want to ask, what is a supercomputer? So there's no definitive definition, but usually it's the three elements that are listed, which is a lot of computational power, so being able to compute a lot of things at the same time. You also need a fast interconnect, so it's a fast network, because you need collaboration, but we will discuss that in a few slides. And usually, supercomputers have very fast and very large storages, because they are shared resources between multiple users, but also because in some situations, you need to process very large files. So let's start with a lot of computational power. What does that mean? Like we mentioned already previously, one computer is generally not enough to solve a lot of real life size problems. So the potential reason is that it just takes too much time to compute on one single machine, and then you need more than one machine, or it could also mean that the memory that is available on your machine is not enough to represent and to allow the processing of your simulation or your experiment. So the solution is to have multiple computers, but acting as one. And the acting as one part is made possible by the interconnect that we will discuss later. I just want to introduce just a few words, a small terminology, because I might use those words, and it's, I think, important that everyone knows what they mean. So usually when we mean a computer, or a computer in HPC, we refer to a computing node. And when we say a blade, we usually mean one or more computing node. If you look at the picture on the right, one blade, so what we will see is one shelf row, can contain one or more computing node. On the picture, we can see three different computers. Then we have those shelf rows. We need to stack them into shelves. A shelf is usually referred as a rack. So it's just a combination of multiple blades or shelves. On the picture, you can see 4 different racks. And if you combine multiple racks, usually it is your supercomputer. So on this picture, you can see 4 racks. Each rack has 20 blades. And in each blade, you have 3 computers. So that would be a total amount of 240 computers. So we have all those computers which are very close to each other, and they need to act as one to run computations on multiple nodes. So to do that, we need a fast interconnect, so a fast network. Why do we need a fast network? Because communication in a network is multiple orders of magnitude slower than accessing the same information in a computer memory. So if we span, or if we distribute computation on multiple nodes, and those nodes need to communicate or exchange information about their own memory to other computers, then we need to have a very, very fast network so that the networking part of the computation does not, let's say, slow down the process to a point where it's not even efficient to use such computer. So usually what we want is a very high bandwidth and a very low latency. So high bandwidth roughly means that you can exchange a large amount of information in a fixed duration of time. So we understand that if the bigger the bandwidth, the more information we can exchange. And what is also very important in supercomputers is to have a very low latency. So the latency in our case is how fast we can exchange one piece of information, how fast we can access the network and send information to that. I got pictures here that represent some simulations that have been conducted at the University of Luxembourg. And usually what is done is that you want to simulate a lot of, let's say here, water particles, and you distribute, so you divide the computation of those particles onto multiple nodes, onto multiple computers. All those computers will deal with, let's say, a sub-problem, but some part of the problem will need to be exchanged between nodes in order to have to allow the computation. So in the on the right picture, we can see how we can split the let's say the whole computation into sub-computation, and we can see where we need to exchange information between computing nodes. Like I mentioned before, we also need to store data, and we need to have a very fast access to data and a large storage. So it's exactly the same as for the interconnect. The storage, accessing data on the storage is very, very slow compared to accessing data from a computer memory. So we need appliances that allows us to access data very rapidly. And because storage on an HPC, on a supercomputer, is a shared resource, we have multiple users accessing the storage at the same time. So to allow that, specific technologies have been developed, specific file systems have been developed, so namely LUST or GPFS. And on the picture, we can see one appliance, so that's also part of the things you put in a rack. And you can see a lot of hard drives that are very densely stacked in that appliance. All right, so now, historically, supercomputers have been really homogeneous in terms of design because in the past, we used a lot of CPUs or processors, and all the different machines, so all the shells were identical. It was because most of the use cases at the time were very, very similar, and they only required CPUs. Nowadays, we see a lot more specialization in those supercomputers. This is because CPUs are great because they can do almost anything, but they are not really specialized. And because they're not specialized, they can be slow for some tasks. And that's what accelerators are for in the, let's say, nowadays designs. There are different types of accelerators, and the more frequent ones are GPU, so it's graphic cards. Graphic cards have been very nice for AI or, let's say, machine learning tasks, but also others. They are much more specialized hardware, so they can do a lot less different things than what CPU can do, but they can do it a lot more rapidly and more efficiently in terms of energy. Then we have FPGAs, which are less frequent. They are even more specialized board that can be reprogrammed and to answer to some very, very specific use cases. And more recently, we're seeing more and more interest for quantum computing. So to perform some tasks which are related to quantum physics. All right. On the next slide, I'm showing one modular design, which is the one from the Luxembourgish national supercomputer called MeluXina. And on this picture, you can see that the design was really splitting the different modules. So they have a regular, let's say, a cluster module. They have an accelerator module containing GPUs, like I mentioned, and also containing FPGAs. And they have also a large memory module or a cloud module. To finish that section, I wanted to just show how they look in some, let's say, European context. So we have, again, the MeluXina supercomputer, and in Finland, we have Lumi, which is, I think, the biggest that we have in Europe at the moment. All right, so now I want to use a supercomputer. How can I do that? So it's slightly different from using a personal computer, but it's quite similar to using cloud resources, at least some cloud resources. But the traditional way of using an HPC is not really via interactive actions like you would have on a regular computer, where you would launch programs, click on it. But it's more, it was historically and still nowadays designed around sharing resources and thus sending jobs in batch and waiting for a resource manager to allocate your job with resources on which your job would then be computed. It's more the traditional way, but currently the mix, the current trend is a mix of interactive and batch. I just want to clarify one thing, just that distinguish supercomputers from cloud services, which is that it's mostly for jobs which have a duration, and thus you can't really, they are not meant to host permanent web services that would constantly run. So I will present the two main ways to do this. The traditional terminal connection, so usually referred as SSH connection. And then I will show the same thing, but using a more modern web portal, so with a browser. The general workflow is first you connect to a login or access node where you will request some resources. Those resources can be some computing nodes. It can be an amount of cores, can be an amount of memory, it can be an amount of GPUs, things like that. And the resource manager will put your request in a queue and check whenever your request can be fulfilled. When your request can be fulfilled, you receive the resources and you can use them. So I will take a simple example of running one program A on a supercomputer. There are, I presented that with 6 steps, but some are similar. So the steps are: first, you transfer your program or your input file. You can, if I use a command line, it would be via the rsync command, but what you need to understand is just it's just about sending some stuff from your local machine to the supercomputer. The second step, when you have your program, is to connect to the login access node, which is where you will request some resources. So here you see how you would connect to the login node on the IAM cluster, which is one of the clusters we have at the University of Luxembourg, and again in a terminal. Then, when you're on this login node, you can submit a job. Usually when you submit a job, you say, this is the program I want to run, so my program, and you state on how many resources you want your program to run. In this a bit complicated case, what I specified is that I want my program to run on 10 computing nodes, so on 10 computers, and I want them to, on each node, I want to have 128 tasks, just because on those nodes we have 128 cores. So my program will run on 1,280 cores, and it will run for 1 hour. I will submit my program, my job, to the resource manager via the sbatch command. And then I can monitor my job. So in this case here, you can see that my job is in the status running with ST and R column. And you can see that I indeed requested 10 nodes, and it's going to be running on the nodes that you can see on the right. So the job has been run. Sorry, I was too fast. When your job is finished, then you can transfer back to your machine, to your personal computer, or you can directly check on the supercomputer what is the results. And with the same technique, if you need to transfer on your local machine the files, you just use the same command as in step 1, but in the opposite direction, and you fetch your files. So that's the traditional command line approach, and I will show you that you can do the same with a portal, which is a web page that you access via your preferred browser. And so I will illustrate that with the on-demand portal that is a popular popular portal. So I log in, I select what I want. So in this case, for example, I want to run the MATLAB program on 128 cores machine. So I select the number of cores I want, and so I select the resources. This will, in the background, will send a resource request to the resource manager, and when it's fulfilled, you will have your program, in this case MATLAB, running onto one machine. And then you can directly access the MATLAB program as if you were on your own machine, but all the computations will be run onto the supercomputer. So that concludes my very short introduction to supercomputers. Thank you for attending the presentation, and if you have questions, do not hesitate to either write something in the discussion tab or add a question in the questions tab.
Well, thank you, Julien, for the nice intro. I think that shed some light at what people can do with the supercomputers, and then also maybe how it works, because that's always the question. Yeah, so for a lot of people, it's still this usina gas. Maybe 1-2 questions that I have that were coming up to my mind. So one thing is, you know, we're still talking about remote access. We're still talking about secure socket shell. There are some trends going in the direction of using it via web interface. But what do you think? Will supercomputing be as easy to use for end users like using commodity programs today? You know, like Excel or Word, or do we always need an expert to operate the whole thing, like we need somebody, an engineer for a steam locomotive?
I think that it will depend on your use case. If what you want to do is something that a lot of people are doing, it's very likely that the web applications with a lot of automation will be available to you, and you will not really need to know much about the engine behind. And the only things that you will need to know is how to use the program that you already use on, for example, your laptop.
Okay.
But if you have something very custom for your needs, or you have very specific needs, probably you will still need to have engineers to run things in an efficient manner on those machines. However, I think the big trend is that more and more people are using the same tools, or tools that are very, very popular, in particular for AI purposes. So I think that a lot of HPC centers or supercomputer centers are trying to facilitate those use cases. I think there are ongoing things at LuxProvide, so who was the MeluXina supercomputer with that regard.
Okay, so you think there will be, let's say, a trend to, how can I call that, appification, where I mean, we've seen that already with DALI or Stable Diffusion, where people can actually use an app to use something which has been deployed, but for creating the large models, it probably would still need that engineering skills.
Yes, yes, I think it's exactly what you said.
Okay. So, and another question that when I was looking at it, because we have come a long, long way, and of course everybody is currently in that super duper hype cycle for the large language models, but where is supercomputing heading? So what will be the next big thing? I mean, you have a little bit higher radar due to the research area that you're in. So what's the big next thing for you in supercomputing?
Well, I think there are multiple things going on, but clearly quantum computing is getting a lot of interest. A lot of supercomputing centers are either ordering or maintaining and using machines right now, using that technology. And at the University of Luxembourg, we are looking for a professor in that field. So there's definitely a lot of interest and a lot of expectation in the field of quantum computing, even though it's still in its infancy. Another aspect of supercomputing is the energy efficiency, because it's very big machines using a lot of electricity. And I think there is more and more interest in making those machines the most efficient in terms of power usage. So probably with specific hardware and specific accelerators, and yeah, that would be the trends I see in that field.
I think we're a long time away from computers running on caffeine and food, which basically powers the human brain. But I think we're going there.
No, it's only for the support people like me. Yes.
Okay. Turning caffeine into code.
Yeah, exactly.
Okay. Well, thanks a lot. So back to the auditorium. I don't think I haven't seen any questions there. Do we have anything? Anybody? Any other questions? Because in the meantime, I would like to point out to our Supercomputing Day over here. So you might want to scan the QR code if you want to register. It's open to everybody. Super duper cool location. I'm sure Julien will be around as well. We'll have a lot of more people over there. So I think your colleague Jonathan will be there as well, talking about some topics. Hackathons, industry will be finding resources like the unicorns for powering your HPC projects, money, everything. So, and of course, we'll have a cool lunch and a cool networking afterwards. So I don't see any further questions. So Julien, thanks a lot for the nice presentation. And I would like to conclude our session having said that. Thanks for watching. See you next time. Stay tuned. Bye-bye.
Bye.